During the Ice Age, North America was a very different place, and roaming across the upper Midwest was a bit more than just your random woolly mammoth. As the Earth warmed and glaciers receded, some of these animals could cope, but many others couldn't, leading to our most recent mass extinction. In this presentation, local educator Nick Wiersum discusses some of these amazing creatures that we, until very recently, shared our region with. Nick will also teach us about some of the most significant discoveries that have been found in our area, including the discovery of the Schaefer mammoth, shedding light on our earliest local human ancestry. Nick Wiersum is a museum educator and paleontologist with a Bachelor of Science degree from UW-Madison in zoology and over 15 years of experience both in the field and at museums. He has spoken at several national conferences, including the American Alliance of Museums and the National Science Teachers Association, and is the curator of natural science education at the Kenosha Public Museums, a Smithsonian affiliate. And with that, please enjoy the presentation.
Thank you so much, everyone, for having me today at the History Center of Forest Lake Bluff. And thank you to George for inviting me to speak tonight. Like you said, I'm a paleontologist. I have a bachelor's in paleozoology from UW-Madison. My background specifically is in dinosaur paleontology. Not the Ice Age, but I'm happy to talk about the Ice Age also. So when specifically my research, when I'm able to fit research projects into my schedule, I'm particularly interested in the connection between dinosaurs and birds, so extinct dinosaurs and modern dinosaurs, and in particular the life histories of the group of dinosaurs, the dromaeosaurs, also known as the raptors. I saw Jurassic Park when I was 6. I'm very interested in velociraptors. No surprise there. So my talk tonight is about what we might think of as a very strange world, though in reality, it's one that was not so different from ours today. But different enough that if we were somehow able to travel back in time just a few thousand years from where we're standing right now, the landscape and the animals inhabiting it would look oddly out of place. Yet little did they know that how much our world would change in just those few thousand years. How exactly that happened is one of the things we're going to talk about tonight. And I'd also like to introduce you to several species of megafauna, that term we'll talk about, with whom we used to share this area. And I know that this talk is called Megafauna of the Midwest, and we are going to focus on local stories, local species. But to understand what happened to them, we're also going to look at that from a global scale, the world at large, because what affects us globally also affects us very locally too. So I'll be highlighting tonight some of the theories with the most evidence that support those theories. And because really, in the end, without a time machine, guesses and theories and evidence are really all that we have to go on. So I don't want to start off by giving you all the impression that the megafauna are extinct. There are lots of animals that we still have on our planet today that we would refer to as megafauna. Here are 2 that exist still today, the African elephant and the ostrich. Here's another, the blue whale, the largest species to have ever known to have existed on our planet. Here's another one, talking to some bison, to some preschools about bison teeth. All of these are animals that weigh 100 pounds or more, which is the lower threshold that we would use to define the term megafauna, except for the preschoolers, but they'll get there someday. So this map we have here looking at here now is an illustration of large mammal distribution across our planet during the last ice age. We see a lot of interesting animals there. And while they primarily show examples of super megafauna, animals weighing over 2,000 pounds, the ones highlighted in gray are those that are still around today. Things like elephants and rhinos in Africa and Southeast Asia. And everything else that we can see on this map here are species that have disappeared. Now you'll notice that we don't have any super megafauna left here in the Americas on this map, where there used to be a lot of them. Though We do, of course, still have some holdovers from the Ice Age, things like bison, our bears, moose, etc. So we still do have a lot of Ice Age holdovers here in the United States and in North America in general. But what does this mean? Well, there have been a lot of losses locally for sure since the Ice Age ended. But I also, like I said, wanted to point out that this is a worldwide phenomenon. And it's not just here in the upper Midwest or North America that we've lost a large portion of our very interesting megafauna in the last 50,000 years. And for the sake of our discussion tonight, we're going to explain the term 50,000 years to the present. We're going to call that near time. As opposed to deep time, which is what I primarily am interested in, primarily study, is deep time, anything older than 50,000 years. But deep time can also be particularly tricky to conceptualize, especially when we throw around, we're going to talk about dinosaurs for just a second, if you'll indulge me. But if we take a look here, we have two different dinosaurs, Stegosaurus over there on the left, Tyrannosaurus Rex here on the right. And in general, we have a tendency to think about all dinosaurs living at the same time together. I blame things like Land Before Time and Jurassic Park, things like that, for giving us that impression. And also because we just casually throw around numbers like 150 million years ago, which is when Stegosaurus was alive at the end of the Jurassic period, or 65.5 million years ago at the end of the Cretaceous period, when you'd be likely to run into a Tyrannosaurus Rex. And when you actually think about those numbers, this is why deep time is hard to think about. When you think about those numbers for just a second, you realize that that means Tyrannosaurus Rex is only 65 million years away from living with us today. It's 85 million years away from living with Stegosaurus. And dinosaurs actually showed up 100 million years before Stegosaurus showed up on our planet. So numbers are big when we're talking about deep time. Luckily, we're just talking about near time, which is a little bit easier for us to grasp, hopefully. So globally, during the last major near time extinction, let's just take a look at what we've lost by the numbers. This is based on several assumptions because we don't actually necessarily have good evidence for the actual totality of losses in these cases. And to be fair, we don't always have accurate estimates of things today, of loss of animal species on our planet today. Every year, there are potentially tens or hundreds or even thousands of species of amphibians that will go extinct in the rainforest before science ever has a chance to discover and describe them. But within the last 50,000 years, this is sort of just like a ballpark of what we lost. Somewhere around 300 to 350 species of mammal, around 1,000 species of birds. With the reptiles, we aren't quite sure. We're a little less clear than the birds and the mammals. Could be more than 100, could be less than 100. Let's just say around 100. And like I said, with amphibians, we don't even know today. So I'm not even going to take a guess over the last 50,000 years. And that's all fine and dandy to just throw some random numbers around willy-nilly. But if we take a detour quick to talk about put some faces to those numbers, to discuss just a few of the amazing local megafauna that have gone extinct in the most recent extinction. If I had sound, I would be playing In the Arms of an Angel by Sarah McLachlan right now. These are the ones we've lost, sort of like that. The year in remembrance at the Oscars, if you will. So first, let's take a look here at the American lion. This was one of the largest cats to have ever existed anywhere on our planet. You can see it here on the right. Next to it there, we have the modern African lion. Significantly larger than their modern African cousins. They were anywhere from 5 to 8.5 feet long, not including the tail, and weighed in somewhere between 400 to 800 pounds. And compared to other Ice Age cats, the American lion had long, slender limbs, and did indeed look very similar to our modern lion, aside from it being much larger. It was certainly one of the most significant predators in the Ice Age landscape, at least the near Ice Age landscape, preying on animals like bison, juvenile mammoths, camels, horses, and yes, even those of our ancestors who were unlucky enough to come face to face with one. I unfortunately don't have an American lion skull with me here. I like to bring one when I can, because when I put it next to the African lion skeleton, very often I will have kids ask me if that's the baby and that's the mama, because the size of them is so drastically different. If you ever get a chance to come up to or visit our public museum, we have the skull of one of them on display, so you can see just how massive these animals were. Now, I can't discuss Ice Age cats, though, without mentioning also probably the most recognizable extinct North American species, the saber-toothed cat Smilodon. These animals were about as long as a modern African lion, but had short, powerful legs, a short tail, and an extremely muscular build compared to other cats, weighing somewhere in between 500 to 1,000 pounds. And where most cats are built for speed, the Smilodon was built much more for brute strength, like a bear, and was probably likely an ambush predator. Its most recognizable features are those 7 to 10 inch long canines that we can see sticking out of its mouth, that it would have used for stabbing its prey, inflicting very serious wounds, and then actually backing off and letting its prey bleed to death before it actually went in to eat them. And since we've talked about lions and tigers, we also have to talk about bears. Oh my. So speaking of bears, I would be remiss if I didn't bring up the giant short-faced bear. These bears, similar to modern spectacle bears, were enormous omnivores. They could weigh up to 1,800 pounds, stand well over 11 feet tall, on their hind legs about 2 feet taller than our modern polar bears. And though like modern bears, females would have been a little bit smaller in those estimates on average. They had these very long paws with very long fingers on them, you can see, especially when compared to things like grizzly bears and black bears that we still find in our in North America today. And the presence of a false thumb on its hand, very similar again to its modern spectacle bear. That would have helped it in accessing and manipulating food, and also for climbing when it could find a tree that could support its weight. Very large, interesting carnivores, all of whom used to live right around here with us. Now, while there were plenty of large carnivores and large predators, there were also a fair number of enormous prey species for them to feed on, such as the giant beaver, whose skull we have up here on the table. You can see a giant beaver here swimming next to its modern counterpart, our modern beavers. So these beavers would be about 7 feet long, nearly 300 to 400 pound beavers that were likely more behaviorally like capybaras or muskrats than modern beavers. Feeding primarily on plants like sedges and other aquatic vegetation, as opposed to the woodier diet we find in modern beavers. And out of all the animals that I'll talk about or highlight tonight, this species is probably the most Midwestern and the most local species. While others were fairly widespread across North America, all the other ones we're going to talk about, the fossils of the giant beaver that we have discovered are actually fairly concentrated around the Great Lakes, in particular in northern Illinois and northern Indiana at the southern tip of Lake Michigan, though they have been found as far north as Alaska. But one of our most surprising Ice Age neighbors would have been these guys, these large Ice Age camels. Was anyone here aware that camels are actually animals that originated here in North America? We tend to associate camels with the Middle East or Northern Africa, but they actually got their start here in North America. These camels, though, as you can see, didn't have very well-defined humps like we see in modern dromedary camels, but their legs were about 20% longer than our average camels today. They stood nearly 8 to 9 feet tall at the shoulder and weighed somewhere over 2,000 pounds. So these huge, enormous camels. And probably my favorite Ice Age neighbor has to be these guys, the giant ground sloth. These were fairly similar in behavior to their modern cousins. I don't like them just because they look like giant Wookiees from Star Wars, but They actually spent precisely 0% of their time hanging upside down in trees. This species, the Jefferson's ground sloth, grew to 8 to 10 feet long, weighed in around 2,300 pounds. And funnily enough, when Thomas Jefferson found their claws in a cave in West Virginia, that was the original discovery, and he's the one who named them, hence them being Jefferson's ground sloth. He attributed the claws actually to the species of a cat. And it wasn't later until the similarity to their South American cousins was noticed. Interestingly, there are places around the world where we find ground sloth fossils, even here in the United States, where you can see in caves where they would take shelter, these long scratch marks along the walls of caves. And scientists, if they get the floor of the caves too wet, or the rain gets the floor of the caves too wet, the caves still smell like sloth poop, even 11,000 years later. And finally, we couldn't talk about the Ice Age without mentioning our largest mammals here in this area, the mammoths. In particular, here we have the Jeffersonian mammoths, which were a bit larger than the woolly mammoths we find a little bit further south. They stood about 10 to 12 feet tall at the shoulder, weighed in between 6 to 8 tons. And mammoths, like modern elephants, have these elongated tusks. But there's curve and cross in front of their trunks there. Each of those tusks, by the way, can weigh up to about 350 pounds. So if you can imagine being an adult mammoth with 700 pounds of tusk hanging off the front of your face, make it maybe a little uncomfortable to move, I think. But they would have used those tusks not only for protecting themselves or showing dominance, but also like a plow, pushing snow out of the way during colder months to reach grasses and plants hiding below there. And interestingly enough, mammoths, while they would have went extinct around here about 12 to 11,000 years ago, they only went extinct as an entire group about 4,000 years ago in northern Siberia, being one of the last strongholds for the mammoths. And sort of just to put that in time, that's about 500 years after the Great Pyramids in Egypt were built. All right, now bouncing back to the notion of these near-time extinctions, we've put some faces to what we've lost now. But this raises a very obvious question. What the heck happened to all our megafauna? And there are many ideas of what happened. There are many theories about what happened. And those ideas are sort of the currency of science, and in particular paleontology. We come up with ideas, we test them, and then we see what comes out being the best idea, which is supported by evidence. That's what science is. So like I said, in the case of our near-time extinctions, there are a lot of ideas, but we're going to sort of sort them together in these 3 big overarching groups. The first ideas that we have about what happened to our megafauna are concerned with climate change. So that really goes along with that exhibit George was mentioning that just left here. What the climate change after the end of the last ice age. Again, the period we're talking about, that near time, about 50,000 years to the present, there was an enormous amount of climate change because it was the end of the ice age, and then we came out into this warming period that we're in currently. Then, after that, there are a number of ideas that say that humans were responsible for a large number of their losses. So we came, we saw, and then we ate everything. And then finally, we have a very scientific category, other. These are the ideas that are kind of unfinished. They are half-baked. They don't hold a lot of water, or some of them are just crazy. But they have been proposed because those first 2, the climate change, human interaction, as we will see, there are some holes in those theories, which is not surprising. But I don't want you to walk out of here just thinking that scientists can't make up their minds about what happened to them. This is just how the process of science actually works. So we accept nothing, we look at the evidence and what it shows us, and then we decide what we're going to accept or what we're going to support based on what the evidence supports. So our positions can change when we're presented with new evidence, which to go back to dinosaurs, is why we think of T-Rex like this, rather than like this image on the right, rather than this image on the left. The image on the left, they did not know what a T-Rex looked like. They looked at a kangaroo and a gorilla and they put the skeleton together, and it's wrong. We now know that T-Rex stood much more horizontally like this. And we also look at the crazy ideas because from time to time, they do tend to make a lot of sense. Just ask Albert Einstein. He had some pretty out there ideas. So to make things even easier for us to keep track of, we're going to shorten those overarching ideas into a single word. First, we'll shorten the implication of human interaction leading to the destruction of all these megafauna species. There's a general term we use for that in the field called the overkill theory. We killed everything. For the sake of continuity with overkill, we're going to move on to the climate change arguments, which we'll refer to by a term that I heard recently and I kind of like. It goes along with overkill. We're going to call it overchill, which is sort of as in we're over the chill of the ice age. It's warming up. And finally, we'll talk about the other theory, in particular, this other theory, that we have the most evidence to support an impact that might have hit the planet about 13,000 years ago. And we'll call that, in the same vein, overkill, overchill, overgrill. Something I tend to do frequently. Don't leave me in charge of the stakes. Since we don't have a clear view about what was really going on and what was really responsible, we're going to look, and we don't have a time machine, like we said. We are just going to look at the evidence that we can collect things like geologic specimens, biological specimens, and biomolecules too, that we can use for things like radiocarbon dating. That's what we have. That's the evidence that we have to put together this narrative of the past. So actually, we're going to start with overchill, that second one, to start. And let's talk about the facts. Now, at some point in your life, I'm sure you've learned about the concept of ecological zonation, though you may not have called it that before. This is basically the fact that the global climate is the warmest near the equator, and the further you travel in either direction, it gets colder. So the closer to the equator, we have our tropics here, then our subtropics. Above that, our temperate regions, and then our polar regions at the top and bottom of our planet. And we tend to think about this as this is the normal distribution of climate across our planet, because this is what we're used to. But if we only go back a little bit, about 25,000 years ago, where we're sitting right now would have been very close, so we can see on this map, to the edge of a large sheet of ice, a large glacier. And when I say large, I mean the edge of it that we would be able to see from here would have been up just north of us, but we would have been able to see the edge of the glacier from here. It would have been about 2 to 2.5 miles tall. And for context, the context I usually give school kids is this: is if you take the Willis Tower in Chicago, you stack it on top of itself 7 times, that's about how tall this glacier was at the edge. In some places further north, it got as thick as 15 miles. So you can see this ice sheet covered the majority of North America, and Eurasia had their own ice sheet, and then down, of course, by Antarctica. Antarctica was just bigger than it is today. We can see how that edge has changed a little bit. So among many other factors, the sheer size of these ice sheets was a huge difference on our planet. Like this exhibit that was just here talked about, though, the ice age wasn't that much colder globally than it is today, only about a 4 degrees Celsius difference, which interestingly, back to dinosaurs. The other way, if you warm our planet up 4 degrees, it's back toward the conditions when the dinosaurs were around, the end of the Cretaceous period, where we had no ice caps whatsoever. But there was so much fresh water locked up in these ice sheets that sea levels were roughly 300 feet below where they are today. And it was much cold because it was so much colder. The evaporation of water over the ocean from ocean currents and things moving around was lessened, meaning that there was less precipitation generally everywhere on the planet. So as you can imagine, that had a huge effect on plant life. So we can, if we sort of look at these different regions here, we can see the changes in where deserts are, grasslands are. In general, they're about where we would expect them to be today, but they've moved a little bit differently. But combining these white and then light blue zones that you can see on this map, you can see the majority of the northern part of our planet was under pretty cold conditions at this point with reduced plant life. And all the other zones that we would normally expect sort of evenly spread out from the equator were packed a lot closer together. We see rainforests are still there, but greatly diminished from their modern expanses. And we can see that in some places too, they're even split up in half, like the Amazon is split in half by grasslands, which is something that's really hard to imagine the Amazon rainforest having a big prairie running through the middle of it today. But the grasslands, which were much more dry adapted, which are much more dry adapted, could expand pretty significantly, as could deserts, and they did. So even though at a glance it might look kind of similar, except for those big ice sheets, this would have been a very different world than the world we see today. So here is an artist's very unrealistic scene of the ice age of the Midwest. A lot of species all crammed in there together. Basically, everything here is extinct, with very few exceptions. See some bison, we see some a moose there, some caribou, some horses, some wolves, bighorn sheep, but there's a lot of things here that are gone from the ice age. And looking at the scene, we see a nice diversity of time, a nice diversity of the animals that would have been around here, though. So the proponents of the climate change theory don't have a great answer as to how climate change on its own could have led to the loss of all of these megafauna in North America. The collapse of these populations that we see in the fossil record occurred over about 400 years, from about 11,000 to 12,000 years ago. The big ice age, the end of the big ice age that we would have expected to lead to these extinctions if climate change were the cause, or solely the cause, occurred about 18,000 years ago. And then again, from then on, we're in this warming period. So how could it be that this incredibly dramatic effect of climate change, the end of the ice age, resulted in very few extinctions? And that was just the last ice age. There were 22 advances and retreats of glacial sheets that we can see over the last 2.5 million years. And during that time, these animals already existed. It wasn't like they waited till the last glaciation to suddenly evolve. They were already here. They weathered those ups and downs of the glaciers retreating and advancing. And they might have seen changes in their range size, how far they traveled for food or the food that was available to them. But the important thing is that they made it through all of that until about 12 to 11,000 years ago. So what could that be what happened to the megafauna? Possibly. But let's consider that while we talk about our next theory, the overkill theory. There were 3 features that seem to be true of this time period, and each of these has evidence to support the overkill theory. The first is that, and there really isn't any disagreement about this at all, is that where extinctions did occur across our planet, there were a lot of them. A lot of stuff died. That's something that even climate change and other theories agree on. And large mammals in particular were much more affected than other groups. Second is that the disappearances didn't occur at the same time everywhere. We see extinctions globally from the ice age, but if it were solely because of climate change, we would have expected to see these animals going extinct at the same time everywhere on the planet at once, and we don't see that happening. And third, when humans spread across the planet from Africa over several 100,000 years, whenever they got to a new place where we hadn't been previously, the next thing that we see happen is everything starts to die. And when it comes to islands in particular, we had an absolutely devastating effect on local populations. So let's take a look at what happened as we spread across the planet. So we originated in Central Africa, in case you are unaware, about 400,000 years ago. And by about 350,000 years ago, we were in Northern Africa. About 250,000 years ago, we had made it up into Europe. And about 65,000 years ago, we had made it down into Australia. A few years after that, about 45,000 years ago, we made it up into northern Siberia there, then up into the Arctic Circle. And we got to the New World sometime around 18 to 16,000 years ago. Not that much time has passed. And in places like the West Indies, New Zealand, Madagascar, it's even sooner than that, or even more recent than that, between about 1,000 to 800 years ago. Now let's take a look at the map of extinctions alongside that human migration. So the first major losses, meaning the species where we see lots of species in a short period of time, was in Australia, where we see those red little explosion marks about 40,000 years ago. Animals were lost about 11 to 12,000 years ago, where we see the yellow across Europe, Asia, and the Americas. And then it's the islands in the Mediterranean, about 10,000 years ago, the West Indies, about 6,000 years ago, and Madagascar around 1,000 years ago when we first got there. And then the South Pacific only a couple hundred years ago. But it's this coupling of human arrivals and megafauna extinctions that gives weight to the argument for human involvement in their disappearance. Now, again, it's not, you'll notice some of the dates, there's some bigger gaps than there are in other places. Like over in Europe, we were there 250,000 years ago. We don't start seeing these huge extinctions until about 11 to 12,000 years ago. But in a lot of these cases, it's very, very quickly after we arrive. But we first saw this pattern of loss in Northern Eurasia and the Americas and on islands around the world. But there were places, you might notice very conspicuously, that we do not see major extinctions. And that would be in Africa and in Southern Asia. Again, humans originated in Africa, and we started moving out of Africa very quickly after we originated. And well, since people arose there, the argument is essentially that we were known to our prey species. The things that we ate knew we were going to eat them. They knew to be leery of us. As we got better at hunting them, they got better at avoiding us. And so as we sort of evolved side by side, as opposed to elsewhere on the globe. And second, in North America, there were about 70 species that went extinct between 11,000 to 12,000 years ago, most of them being megafauna species. And you think that if there was a mass slaughter, that there would be an abundance of these kill sites, just bones and corpses everywhere. But we don't see that. Instead, what we see is the occasional evidence of hunting. And for those who support this theory, the rebuttal for that argument is that, well, the absence of evidence is not the evidence of absence, which is a pretty weak argument. That really doesn't hold much water with anybody else. In any of these instances, though, we would expect to see a lot of bodies, and we just don't see that. But a little bit of local evidence, though. Well, first, let's imagine that you've recently arrived in North America, being us humans. We've recently arrived in North America, and we are traveling across the Bering Land Bridge, and you're seeing all these big mammals that no one's ever seen before. And they look at you, or us or our ancestors, and they see these awkward looking, mostly hairless animals walking on two legs. They have no big sharp teeth. They don't have any imposing horns. They're carrying sticks for some reason, but it's really just like, well, what's that all about? And the idea here being borrowed from modern ecology is a concept called behavioral naivete, meaning that really, unless you have a reason to be afraid of another animal due to things like predation, as an animal, you're not really going to recognize the threat of a new predator moving into your environment, particularly one as goofy looking as us. You can ask the dodos. Meanwhile, humans are just seeing tons of walking barbecues. And we hypothesized that if we weren't already big game hunters at this point, when we arrived in the New World, we quickly became them. And humans did what humans love to do. We went and controlled all the resources, and we reproduced very quickly. We're very good at doing those two things. So there would have been a huge explosion in our own populations. Again, okay, so moving to, this is the aside I wanted to get to. Because this talking about, well, we don't find evidence of hunting and stuff, we find the occasional evidence of hunting. That's what I want to talk about, because it's one of our museum's claims to fame up in Kenosha, and also one of the more significant anthropological discoveries that has been made in the upper Midwest concerning the end of the Ice Age. And it's what we've dubbed the Schaefer site, or the Schaefer mammoth. It's called that because it was discovered on the Schaefer family farm. It's awe-inspiring sometimes how we are able to come up with the names for these things. Anyway, so a quick story about how it was discovered. Back in 1965, a farmhand was driving his tractor through a field, digging a small drainage trench on the edge of one of the fields, which we can see here, this big dark black line there. That's the pipe, a pipe running through it there. When he hit something hard, it flew up into the wheel well of his tractor. It jammed it up, and it almost threw him off the tractor. It was so abrupt. But he got down, he pulled out this big, weird, strange looking rock. And he brought it up to the farmhouse. They washed it off, and they went, "That's a really interesting looking rock." And they used it as a doorstop for the next 20 plus years. And then one day in 1989, the grandson of Mr. Schaefer went to him and said, "I don't think that that's a rock. I think we should have someone take a look at it." So they called our museum. We went out to take a look at it, and we instantly recognized that it was indeed not a rock. It was a piece of a mammoth tusk. So we got to work excavating this mammoth out of his field, bringing it back to the museum to study. And during the excavation, the thing that got the archaeologists and the paleontologists who were working on it really excited was that amongst the bones, there were a number of lithic or stone tools buried in and mixed amongst the bones themselves. So along with those tools, there were also finding these delicate cut marks on the bones from the people that had hunted and butchered this mammoth. And incredibly, we were able to determine that this mammoth was hunted and butchered by what we term the pre-Clovis people about 14,500 years ago, which, as you may recall, is only about 1,500 years after humans were even thought to have made it to North America. Prior to us finding this site, one of the reasons it had such huge implications for modern archaeology is because prior to us finding this site, we had theorized that maybe humans were here in the upper Midwest about 10,000 years ago. That seemed like a good estimate. We had gotten to North America, give us a few thousand years to expand and leave our mark where we could find it. But this is way earlier than we thought it was even possible for humans to be here. So it's a really interesting kill site. If you want to see a big, disgusting diorama of what it would have looked like as people chopped up a dead mammoth and went inside it and scooped its guts out, we have one of those at our museum. You can come check out. All right, now finally, let's really quickly talk about that last theory, overkill We're not going to spend a lot of time on it because I don't think since it's fairly similar to other theories about mass extinctions, you've probably heard before. We don't need to spend a lot of time really pushing the evidence for this, really explaining what would have happened. So you've probably heard of mass extinctions like this before, particularly the end Cretaceous extinction about 65.5 million years ago, bringing it back to dinosaurs. When an asteroid hit our planet off the coast of the Yucatan Peninsula, and just huge explosion. Huge explosion, dust clouds, earthquakes, volcanoes. We estimate that, it hit off the coast of the Yucatan Peninsula, where Cancun is. Dinosaurs at this time, and animals at this time in Montana, minutes after this asteroid hit, the air temperature would have changed almost instantly from about 70 to 80 degrees to about 700 degrees, like cooking animals alive thousands of miles away from the impact site. It killed a lot of stuff. And it took out about 75% of the species on our planet. The parallel argument for what happened at the Megafauna at the end of the Ice Age is that a similar impact hit our planet about 13,000 years ago. And wherever it hit, because we don't know where it hit, it did the same thing, but on a much smaller scale. And we do have some evidence that we find for an impact around this time. One of the pieces of evidence we find are things like this, shocked quartz, which you can see this abrupt change in the crystalline structure of quartz crystals from around that time that can show the change in the strength of the impact, but also just their mere presence shows the presence of an impact at all. Or like this seen from the southwestern part of the United States, we find these carbon-rich, what we call black mats. So we see this dark line running through the middle of the rock there, which supporters suggest show evidence of widespread wildfires caused by this impact. So while it's possible that an impact at this time there was an impact at this time, the question for us is, did it cause those extinctions? Did it even contribute at all to the elimination of species across the planet? And you probably won't be surprised to hear me say we don't know. We do have an idea why large mammals would have been impacted in particular. And it's easy for us to understand why large mammals would have been impacted by a large asteroid impact like this, because we're large mammals. And large mammals share a lot of similar traits across our life history that could cause several problems for the megafauna of the Ice Age. Things like our gestational periods are long. For us, it's 9 months. For animals larger, like elephants or mammoths, we're looking at 22 to 24 months gestational period for them to have a new offspring. Typically, at least in relation to smaller species, we take a long time to mature. Again, if we look at elephants, it takes them about 10 to 12 years, modern African elephants, about 10 to 12 years for an elephant to become sexually mature. For Asian elephants, it's even longer, 12 to 14 years. We live a long time, which is a positive for us. If you need to wait these long times to mature and to have offspring, living a long time is a positive. But most of our births are single. When you look at megafauna, we're having one baby, one offspring. So this could be an issue. If our populations take a big hit at a certain point in our life cycle, it can take a very long time to bounce back. So all of these arguments too can point to why it's bad to be big, not just traits that could be affected by an impact from outer space. But these are just risks that nature throws at you for being big, for the curse of being born big. Now, after spending all of this time talking about all these theories, I want to propose just one more that we didn't mention yet, which is since we don't know the whole story, and since there are arguments for and against all of the ideas, maybe the best conclusion is that it was a combination of them. Maybe that's just me trying to be a people pleaser because I'm a middle child and a Libra. But at this point, I think it's because our understanding of these megafauna extinctions, there really isn't a point to being very rigidly held to supporting one of these ideas over the other. We just don't have enough evidence, and they all might have played a role. Now, you might be thinking, sitting there and thinking to yourself, Nick, this is all very interesting. You're an incredible speaker, but why should we care about any of this? Why these animals are all extinct? What happened to them? It's interesting. Who cares? It's in the past. Well, first, thank you very much. It's very kind of you, but the reason why this is still a great puzzle for us to think about and to spend our time on is because it does have implications for our own future. The same reason why we study climate change today. Why should any of us be particularly worried about the surviving megafauna on our planet today? Not to get too doom and gloom at the end here, but many of us, not just in the scientific community, can sort of see the writing on the wall. If we continue down the path that we are on right now as humans, taking resources wherever we feel like it, doing whatever we want while ignoring our impact on the planet, the community, the global climate, the global community, inevitably, it's our existing megafauna that are on our planet still who are going to suffer the most. And as a reminder, hopefully you'll recall that includes us. Thank you very much.
Can you talk about the extinction of horses? Because I had seen a YouTube video or a TED talk on camels, so I knew about that.
Sure.
But, you know, I think there's like a ton of myths about horses when they were in North America. So you see all these pictures about when Columbus came over and the Spaniards introduced horses, but
Right.
we've seen, you know, you had pictures of horses being there before the Ice Age.
Yeah.
Can you talk about that?
Absolutely. So horses actually originated in South America. That's where we find their origins. About 2.5 to 3 million years ago, we saw what was something that was called the Great American Interchange, where we had all these mammals from South America. This is right when Panama finally connected North and South America, where all these animals from South America migrate north, and all these mammals from North America migrate south. So horses are one of those animals that came up from South America, and we see sort of really take over a lot of ecological niches in those grasslands that form in the Ice Age. During the Ice Age, they evolved here. Primarily, they really took off in their evolution here as a group, but then as soon as that Bering Land Bridge forms, they peace out. For whatever reason, they leave North America and they travel across that Bering Land Bridge and mostly go extinct here prior to humans arriving. Mostly prior to humans arriving here in North America. So maybe like walk past each other on the Bering Land Bridge, but they migrate across the Bering Land Bridge into Asia and then eventually into Europe. And then again, right, then the Spaniards bring them back. They couldn't get away for very long. We don't really know why they left. No, same reason we don't really know why sloths left South America and came up to North America, or why llamas and alpacas went from North America down to South America, because they originated here too. So we gave South America our alpacas, they gave us their horses, our horses left, their alpacas stayed.
One around the plant person that
Sure.
that was a silica, the grasses fought back, then got more silica, and the horses couldn't handle it, and the sheep couldn't make it in time.
Yeah, for sure.
That was my question to you too, was this whole extinction theory, what's happening to the plant? What are we learning from pollen studies and climate to know, was it all, I mean, I think that like you said, it's a combination, but
Right.
what pressure on what these big things are eating.
For sure.
It could weaken them, allowed us to tip the scale.
Yeah, and here, if I
What's
can,
the evidence there, what they pose us eating them.
if I can
Yeah.
jump back to my ecological zonation. So if we take a look at North America. Over North America, we see primarily there's this large grassland in the middle. Sort of, there's a couple of these smaller ice sheets in the middle of that grassland. We see some desert then on the edge of that grassland and along the California and Mexican coast there, the Pacific coast. And we see this very small band of woodland running basically by the Rockies and then over here in the southeastern part of the United States. The rest of the continent was primarily grasses and very dry, hard, dry adapted plants, right, with large silica content. When we look at trees, because that was one of the things we studied too when we studied our mammoth site, is we did look at pollen that we found mixed in with the rock and the clay in the site. And we found a large number of pine pollen, or specifically white spruce, and a lot lower levels of things like oak and maple and birch, things that we associate now with the upper Midwest and our temperate forests, but they really didn't exist. And the pollen levels that we do find from that time period show that there weren't a lot of trees around. What were here were hardier evergreen trees. There were very few deciduous trees sort of speckled in every now and then. But yeah, the primary things that we would have seen around here would have been grasses, all types of lots of types of grasses, primarily grasses and then sedges and things like that.
Any final?
Yeah.
Do people like yourself, scientists, ever sit around and speculate how much time we have left on this planet?
Yes. Not because I'm a scientist, but yes. We do, but it's also, it's that thing, it's a thing of, I think we tend to think of it a little bit like, it's great thinking back and hypothesizing what happened to these things. We actually have evidence for that. We have no evidence from the future that someone has sent back to us to show us where our planet is headed. Can we look at trends? Absolutely. We can look at trends, and we can look at how global temperatures have changed, how how emissions and things have changed, the content or the makeup of our atmosphere. We can look at how our temperature and how the climate environments have been affected as we move across the planet now, and as we industrialize. If we look at when we look at Europe, for example, from about the year 1300 to about right at the start of the Industrial Revolution, Europe actually went through what we call a mini ice age. Temperature plummeted from what it was. It got a lot colder than it is today. And then the Industrial Revolution started and sort of shot us out of that. Even a few short years, we could see the climate in Europe changing and warming up from what had happened the previous 500 years, essentially. So while we don't like to speculate necessarily on what is going to happen, there are things we can look at. So we can look at where temperatures are going. We can look at where our atmosphere is going. We can worry about things like the asteroid Apophis. Have you ever heard of Apophis before? So it's an asteroid that, if it comes, there's a little keyhole that's several 100,000 miles wide. That if this asteroid Apophis, which is passing us in the next 7 years, if it goes through that keyhole, it will miss us in 7 years. It will definitely hit us 9 years after that, though, and it's big, so that's not great. So we think about things like that, but in terms of like looking at where the climate was and things during the ice age and trying to speculate where we will be in 100 years, 1 billion years, we have estimates of like, and we have estimates of like tectonically how the plates of our planet will move around. Like I know, looking at trends and looking at the geologic evidence that in about 300 million years, Russia is going to eat California. We're gonna get pushed underneath Russia. California is gonna snap off and it's gonna get pushed underneath the eastern coast of Asia. You know, we know that every year the Atlantic Ocean is getting bigger and the Pacific Ocean is getting smaller. Which I think the airline companies are on too. So like, it's only this much more, you have to fly this much further this year. Only about 1/4 of an inch a year, but those stack up. But yeah, hopefully that answers your question.